Okay, so this is part of my classical mechanics course, and we're getting into line integrals. So let's start with the simplest case. Well, not okay. It's not the simplest case. That was a lie. I just lied to you. I apologize. A easier case of a line integral by looking at an example of an object falling towards the moon. Okay, so let me just do a quick physics review here. So suppose I have the moon. See, it's got craters on there. See, that's what that is. This is the moon. It has a radius r. I don't really care. And I have, let's say, a rock right here, and it's going to start at position r1, and it's going to fall to r2. And so one way that I could calculate the speed at position 2 is to use the work energy principle. So the work energy principle says that in this system of the moon plus the rock, and I'm going to assume the moon's stationary, not exactly true, but that's fine. The work is a change in kinetic energy, where the kinetic energy is 1/2 mv squared. So if I calculate the work done on this rock going from position 1 to 2, then I can calculate the change in kinetic energy and the final speed. Now, but here's the deal. Work is defined as a line integral. And this is a not crazy difficult line integral. We'll do those in a little bit, don't worry. But we define work as the path integral, line integral, from position 1 to 2 of f dot dr. Because see, f is a vector and dr is a vector. So you got to take the dot product of two vectors because you can't integrate. Well, you kind of can, but you can't. We want to integrate just one single. We want to get a scalar work value. Okay, so I want to do this two ways. And I think I'm going to do it numerically first. I think that will make the most sense, and then we'll do it analytically. So if I have a rock right here, I have the gravitational force. If I have the vector locating the rock as the position vector r, and this is in the x direction. Okay, let's just make it simple. That's in the x direction. The gravitational field is negative g. That's a constant. Mass of the moon, I looked that up for you. Mass of the rock, let's say it's 1 kilogram, don't really care, divided by the distance between them squared, and then I have to multiply by this r hat to make it a vector. Okay, and then if I use that, I can use dr as a vector, right? It's also, and I can take the dot product, and then I can integrate. And so that can bring up some problems, but let's do this numerically in Python, and then I think it really helps to make sense. Because in Python, what we're going to do is to not integrate. Instead, we're going to do it a finite number of times. So let's start again. Here's the moon. There's my final position. Here's my initial position. So what I want to do is to take my rock and let it move some distance right there. It's going to move that distance. So let's say delta r, and let's call this the x-axis. Delta r is going to be the vector negative 100 meters, 0, 0 meters. It's going to move that far in the x direction. That's my displacement. And so the problem here is that I can't take the dot product and be done with it because the force changes. But if I have a small distance, and that's fairly small compared to these distances I'm dealing with, I can assume f is constant. So I can say f equals negative g, mass of the moon, mass of the thing, over, and let's just call this x squared, and then times the vector 1, 0, 0, or have the negative sign. I do need that, right? It's going that way. The displacement's in the same direction. So if that, I can say delta w equals f dot delta r, right? That's the work done over that path. Then I can move my rock right there and then do it again for another delta r. And then I'll calculate another delta w. And then I'll do it again, and I'll calculate all these works over the little path, and then the total work will just be the sum of delta w. Does that make sense? I think I like it that way. A couple things we can look at. One, is work positive? In this case, it should be, right? Because this is a vector in the negative x direction. This is a vector in the negative x direction. So when I take the dot product, that should be positive. And that means that the speed is increasing. So that's good. Okay, so let's just write down some stuff here and then put it in Python. Mass of the moon. I'm using the moon because I don't have to worry about the air. Okay, the moon has no air. 7.348 times 10 to the 22 kilograms. M of the thing is 1. I'll just pick that. The radius of the moon doesn't really matter, but it's 6.67. No, it's not. It's 1.737 times 10 to the 6th, 10 meters. And then G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And then I'm going to go from R1, let's say, we'll write it right here. R1 is 3 times the radius of the moon. R2 is 2 times the radius of the moon. And V1 is 0. So I can find out how fast it's going. So I'm going to do that and get a numerical value. And then we'll do it analytically and see how that compares. So let's switch back over here to Python and get some stuff done. Okay, so this is, I'm going to give you the code here. You know I give code. So this is Web VPython in Trinket. So you don't have to install anything. So what I'm going to do is enter my values here. So mass of the moon is 7.348 times 10 to the 22nd. Radius of the moon, 1.737 times 10 to the times 10 to the 6th. G is 6.67 times 10 to the negative 11th. And then M is 1. And then R1 is 3 times radius of the moon. R2 is 2 times the radius of the moon. And let's do V1 is 0. That's not a vector, right? Because if I use the work energy principle, it gives me a scalar answer. It doesn't give me a vector value. Okay, so now what I need to do is get a vector value for the position of my rock and a vector value for dr, and then I can start calculating the work. So let's say r, where it is, I'm just going to call it r, it's the vector r1, 0, 0. That's where it's going to start. Okay. And then I can say dr is the vector negative 100, 0, 0. And we can change that later and see what happens. Now, I do need one other thing. I'm going to go through a loop, and in each of these steps, I'm going to calculate the work delta W. But then I need the total work, so I need to add it to something. So I need to start with something. So I'm going to start with this. Work equals 0. So now when I calculate it, I can add it in there. So now I'm going to make a loop. So while r dot x is greater than r2, right? So r dot x is the x position of the vector r. And so what I'm going to do is keep moving that closer and closer and closer to the moon until it's no longer greater than r2. That's how I'm going to do that. So the first thing I'm going to do is to calculate the gravitational force on the rock at that position, which I'm assuming is constant during this time interval. Not this distance interval, it's a distance interval. So F is negative g times mass of the moon times m times norm r, right? So norm is a unit vector in the direction of r. And so that so the r is pointing away from the moon. So the negative means it's pulling it towards it. This is the force on the rock, not on the moon. And then I need to divide by the magnitude of r squared. Now I can calculate the work done along that path. I know delta r, I'm calling it dr. I know F, so I can say dw. I say d instead of delta because it's easier to write d. D is delta. Is that okay? Okay. So this is going to be the dot product of F dot dr. Dot product is built into Python. No. Dot product is built into Web VPython. So that's good. So it's going to be equal to dot F dr. That's it. Now I need to add that to my total work. Work equals work plus dw. So I'm going to take whatever value I had at the end of the last loop, or starting at 0, add that dw to it. And then I'll just keep on doing this. This is an integral. It's just like an integral, except my step size doesn't approach 0. It's 100. Okay, now I need to move my rock. So I'm going to say r equals r plus dr. Now, it's plus, right, because dr has a negative x value. So that will move it closer and closer to the moon. I think that should be it. That will give the total work. So let's just print that. Print work equals work joules. And let's go ahead and calculate the final speed. So V2, let's do this. K2, the kinetic energy at 2, is going to be K1, the kinetic energy at 1, plus work. And then I can use that K. I'm just writing it out because it's easier to see. I can use that K to find the velocity. So V2 is going to be 2 times K2 divided by m square root. And let's print that. Print V2. And we don't really need that, but just to have something to do meters per second. And let's run this sucker. Okay, so that's... Oh, it didn't print it. K1, okay. K1 equals 0.5 times m times V1 squared. Sorry. Okay, so it's going. Oh, it's kind of fast. Yeah, but it went like almost. It went the radius of the moon falling towards the moon. Okay, so that's the work done is positive. That's the final speed is faster than 0. Both those things make me happy. Now we could make a graph of the speed as a function of time, and I will do that at the end. I just promise you that. I'm going to do it. Okay, but now let's do this same problem as an integral, and then compare our value right here. So let's switch back over to paper. Okay, so I'm going to draw a picture again. So here's my origin. There's my moon. Here's R2. Here's R1. And then I have the force is that way. But I'm just going to go ahead and write F is going to be equal to, and this is the x direction. So I'm going to write this as a Cartesian coordinate vector, negative g mass of the moon mass over x squared, and I didn't even need to do that, right? Because I'm only moving in the x direction, so I've squashed it all to x, and that's it. Well, x hat, yeah, that'd be right. Or you could say times the vector 1, 0, 0. That is x hat. dr in Cartesian coordinates is the vector dx, dy, dz. Now, I'll go ahead and warn you because I make this mistake all the time. You might be saying, well, shouldn't there be a negative sign there? No, because this is the dr in Cartesian coordinates. The direction of the integration comes from the limits of integration and the path, right? Which we just say in a straight line. The path won't come into play here, but in later problems we'll do path. So work is the integral from, now I'm going to say x1 equals r1, x2 equals r2 of f dot dr. Well, let's go ahead and take that dot product. I have two vectors. If I take this dot product, I'm going to get this vector, this times dx, 0 times dy, 0 times dz. So I get the integral of negative g m of the moon m over x squared dx from r1 to r2. Okay, so now let's go ahead and let's do this. Let's pull that stuff out front. Negative g m over, no, r1, r2, dx over x squared. So I can integrate 1 over x squared. It's going to be negative 1 over x, right? Because if you take the derivative of negative 1 over x, you get 1 over x squared. That's right? If I take the derivative, that's right, I get this. Yeah. I always make that mistake. I got it. So now I get, excuse me, negative g m over x from r1 to r2. And so let's evaluate that the limits. I get negative g mass of the moon mass over, that's it, 1 over the final r2 minus 1 over r1. So is this going to be positive or negative? Let's just check that real quick. So R2 is right here. So it's a smaller number. So this is going to be, oh, this is gone. I'm sorry. When I integrate it, I get negative, so that's gone. So I do get, this number is going to be larger than that because R1 is larger. So this whole thing will be positive. So that's good. So that's going to be the work done. I'm going to calculate the work this way, and then we can compare it to the other work. And then we don't even need to calculate the speed because who really cares? Okay. But that's a line integral analytically. So let's compare the two answers. I'm going to calculate this in Python. I'm just going to type that equation in, and then we can make a comparison. And then, like I said, I'll make a graph of speed versus time. Okay, back to Python. So right over here. So let's just calculate down here. I'm going to say WT for theoretical work. It's going to be equal to G times the mass of the moon times M times 1 over R2 minus 1 over R1. And let's print that. Print, I even call it WT equals, comma, WT joules. Is that a win? That's a win. 4.070255 times 10 to the fifth, 4.702266 e to the fifth. That's the same thing. So yeah, you can fix that, right? And we're not going to get the exact value, but if I want to, I can make this a smaller step size and then run that. It's pretty close, right? I mean, that's pretty close. That's close. Okay, I told you I'd make a graph, so let's do that real quick. This is just a bonus. So I'm going to go up here, G1 equals graph. I'm going to make a graph of position, as speed as a function of position. So title, falling to moon. That's fine. X title is going to be equal to, it's position graph, right? So X title is going to be equal to, I'm going to call it R in meters, distance from the moon. And then Y title is going to be equal to V in meters per second. And then I need to do this. Width equals 500. Height equals 250. I mean, you don't have to do that, but the graphs end up too big for this resolution. I'm at a lower resolution. Now I need something to plot. F1 equals G curve. Color equals color dot blue. Oh, and then I'm going to show you one other thing. I'm sorry. I will show you one other thing on paper. So down here, now I have my V1. Let's just say V equals 0. That's the starting speed. Okay. Now what I'm going to do is once I calculate this work done, I need to calculate the new speed. So I can say V, let's say K equals K1 plus dW, right? That's the change in energy. And then I can use that to calculate the velocity. V equals square root of 2 times K divided by M. Now I want to plot that. So F1.plot, let's just do R.X. I could do mag of R, which I probably should do. Mag R is R.X versus V. And let's see if that works. Please work. Okay, so there you go. So there's your curve. Now, one thing you'll notice is that it actually starts over here, right? Because this is position versus time. It starts right there. It's not and it actually moves this way. So that's the final position, right? The final speed right there. One more thing. Let's go back to the paper, and I'm going to show you one more thing. So let's take this. And what if I want to find the work going to a distance R2 starting with R1 going to infinity? So if I start at an infinite distance away and let it fall down to R2, well, over here all I have to do is let R1 go to infinity. If R1 goes to infinity, that's gone, right? This is approximately 0. So the work done would be G, mass of the moon, mass over R2. Now, remember that if I take the system consisting of the moon and the earth, and it doesn't depend, and the work does not depend on the path, which it doesn't in this case, then I can turn this work into a potential energy. I can say delta U is going to be negative the work. So that means that delta U is negative G M over R2. And this is where we get U equals negative G mass of the moon mass over r as the gravitational potential with respect to infinity for gravitational objects. Okay, this is really a delta, right? But here we have the other point is at infinity, where we set the potential at infinity is equal to 0. We set that. And then we have this as the potential with respect to infinity. So that's where that comes from. It comes from that line integral. I just wanted to show you that. Okay, I did the graph. I did the potential, line integral. We'll do some more interesting line integrals on the next episode of this physics stuff, whatever it's called. Okay. Oh, and if you want to look at the other videos in my classical mechanics series, I'll include a link to the playlist down below.